Hello, students. In this video, we'll be discussing phase diagrams and how we can read them. So basically, remember, a phase is pretty much the state of matter, solid, liquid, or gas. And you may remember in our discussion on the effects of intermolecular forces, we had a vapor pressure curve where we showed the pressure versus temperature, and we showed the vapor pressure curve of different substances. Now, all along this vapor pressure curve is the vaporization curve, and that's what basically means is simultaneously at that temperature, I can have a liquid or a gas, and that's what the vaporization curve shows me. At a given temperature and pressure, I could have in equilibrium evaporation and condensation. So with the phase diagram, we just have an extension of this. So again, you would still have your axes of temperature, and we'll just do degrees Celsius and pressure. And the way the phase diagram curve looks like is this is only a portion. If I draw the whole curve, it pretty much looks like, you can think of it as like a fork, right? It kind of looks like that. And when we look at that, it's splitting it up into three phases. So what do I mean three phases? In this area, this is my solid. So typically under lower temperatures and lower pressures, I tend to have this solid phase. Now in the interior of the fork is where I would find a liquid phase. And then in this exterior, this would be a gas phase. And this vapor pressure curve that was shown earlier is this right here. This curve right here would be my vapor pressure curve, right? And we've discussed heats of vaporization. Now, along this curve, right, we see it's between solid and liquid. So it's not the vapor pressure curve because that's between a liquid and a gas, evaporation and condensation. But here I see melting and fusion. So this would be what my fusion curve is. So at a given pressure, I'll just make one up, and a given temperature right there, I would simultaneously in equilibrium, I could have both states. I could have a solid and a liquid depending on how much energy is put into the system and separating the molecules and disrupting those intermolecular forces and making sure that there is a greater distance, a greater amount of potential energy to convert it. Now, there's a couple other points when you look at these phase diagrams that you need to take in consideration. So another point is right here. And again, this side is the gas. It's not in the interior of the fork or on the other side. So this curve right here would be my sublimation curve. So remember, sublimation is where a solid goes straight into the gas phase. We see that with carbon dioxide, dry ice. We see that with iodine, but it's a straight sublimation. Another important point is this point right here. This point is referred to the triple point. The triple point of a phase diagram is where you can have all three phases of matter at that pressure and temperature. So at this point right here, I could have solid, liquid, and a gas all in equilibrium simultaneously. The other point of topic is this point right here. Now, again, I didn't draw this to scale, okay? But just to give you an understanding, this is referred to as my critical point. Now, the critical point is extremely important because this is where a liquid and gas, if they're in a closed system, they will eventually reach this critical point and merge into a single phase. There won't be two distinct layers of gas and liquid. The single phase will be one thing, and that's considered your supercritical fluid. Beyond this temperature of where the critical point is, the single phase will be known as the supercritical fluid, and it will exhibit both liquid and gas characteristics. So to start the phase diagram discussion and how to read these, we talk about supercritical fluid. And again, if I take a liquid and I put it in a sealed container and I heat it up, as more of the vapor collects, it's going to increase the pressure inside the container, right? And eventually, the density of the vapor above the liquid is going to increase more and more, and the density of the liquid is going to decrease, where they're going to reach a point where there is no meniscus. There is no separation of phase. And at that temperature, we form what's referred to as a supercritical fluid, one state. The supercritical fluid has both properties of gas and liquid. Now, the critical point, which we discussed on that phase diagram, is the temperature required to produce that supercritical fluid. The pressure would be called critical pressure. At the critical temperature or higher temperatures, the gas can't be condensed anymore. So you will just have, at that point, the supercritical fluid. But let's go reading into the phase diagrams a little more. So again, they describe the different states of matter and not just showing you where the solids and liquids and gases can be found at given temperatures and pressures, but it also showed you the state changes or the vapor pressure curve, the vaporization curve, the fusion curve, and the sublimation curve. So here is a phase diagram of water. And again, we see that, that fork, and it's separated into solid, liquid, and gas. Now, each region represents the state. The lines are going to represent the state changes that we've already talked about. So, this line between the liquid and the gas is the vaporization. Between the solid and the liquid, that line is the fusion, where we see the melting and the freezing. And this line between the solid and the gas is sublimation. At that point, you can have both states. The critical point, again, is that far point. The triple point is where I can have all three. And there's a few more things that I want to show you, especially with the phase diagram of water, which is, one that we're familiar with. At 760 torr, really, we know that as the standard pressure of 1 atmosphere. We see when we go across here that at this point, the solid begins to melt at what point? The melting point for water at 1 atmospheric pressure is 0 degrees Celsius. Now, if I keep adding more and more heat, eventually that liquid is going to heat up, all the way to this point. And at that point, it's going to begin to vaporize and boil. And what is that point at 1 atmosphere? Well, if I drop down, that temperature is my boiling point. So you can use the 1 atmospheric of pressure to take a phase diagram and determine the freezing point and boiling point. Now, the other thing I want you to notice is typically the fusion curve or the freezing point is going to increase as pressure increases. And typically, and especially the way I drew it, and you'll see in all other phase diagrams, that fusion curve has a positive slope. Water is unique. Water's fusion curve is actually a negative slope. And the reason is water is more dense than solid ice. So liquid water is more dense than solid ice. So ice is less dense. The solid is less dense because it has an open lattice cage structure. That's unique. All other substances, the solids are more dense. So as a result, when we increase pressure, okay, on the surface of ice, it causes it to melt because we're squeezing it down and we're actually making the particles get closer. So as we increase pressure and force it to get closer and melt it, we can have a lower temperature. So that's what's unique about water and its phase diagram. So water has a negative fusion curve where other substances have a positive. So we're using water again just because people are comfortable. But what it's showing you is, if I started at, let's say this is negative uh, 20 degrees Celsius, okay? And I'm at 1 atmosphere. If I heat it up to 25 degrees Celsius, what's going to happen? Well, I'm going to move along 1 atmosphere all the way up to 25. So eventually, to get to 25 degrees Celsius, I have to heat up the solid, melt it, and then heat up the liquid, which starts at 0 all the way to 25 degrees Celsius. Now, I can keep going. I can go beyond all the way up to 100. I begin to boil and then to 110 or whatever, and then I'm a gas. Or I can go from this point and say, well, what if I decrease pressure? Well, if I decrease pressure enough, right? And if there's not a lot of pressure above my liquid, as I learned earlier, it's going to be much easier for the molecules in the bulk of the liquid to escape and reach that escape energy or velocity to overcome intermolecular forces and vaporize. So at 25 degrees Celsius, if I decrease pressure enough above the liquid, I'll become a gas phase. So that's essentially how you're reading these phase diagrams. Okay, where am I located? What state of matter or what line, what curve where I have two states simultaneously? Okay, so again, different phase diagrams, similar shape, same concept. So here I have iodine, has a critical point, has a triple point, solid, liquid, gas, vaporization curve, fusion curve, sublimation. Now, 1 atmosphere, right? I see that, I can get to the point right here. If I go to carbon dioxide, same thing. What I notice at 1 atmosphere, carbon dioxide at 1 atmosphere, as I heat it up, because a triple point is at a higher pressure, I go straight from solid to gas. So I'm cutting across this sublimation curve, and that's why I see dry ice sublimating. So what if you had a problem and it asked something like, what phases are present at point F on the given phase diagram? So the first thing is you got to find point F, and point F is right here. And we know that this is a solid, liquid, and a gas, but point F is specifically on the curve between a liquid and a gas. So that's my vaporization curve. So what can happen? Well, I can have a gas and a liquid at a point of vaporization. Now, if I was at point A, I would only have a solid. Point C, I would only have a gas. Point B, I would only have a liquid. D, I've passed the critical point, so I would have the supercritical fluid, right? E, heat of fusion, solid and a liquid. G, triple point, solid, liquid, and a gas. So it's really easy once you understand the phase diagram to identify what happens. So let's consider another phase diagram of uranium hexafluoride and which of the following conditions are true. At 1 atmosphere, UF6, uranium hexafluoride, boils. So at 1 atmosphere, if I go across, well, even if I increase temperature, I go from a solid straight to a gas. This curve is my sublimation curve. So it doesn't really boil, it sublimates. Does it melt at 1 atmosphere? No. Melting means going from a solid to a liquid. And then, does it sublime? Or does it boil? Boil is going from a liquid to a solid. So the answer is C, it sublimes. So I hope this video makes sense. And yeah, Phase diagrams, they're fun to read, they're pretty straightforward. Let me know if you have any questions. Thanks.